Set up here.
Recording started.
My name is Jim Caldwell. I'm CEO of Workforce Incubator. We're a nonprofit headquartered in the East Bay of the California, San Francisco Bay Area, and we're what's called a workforce intermediary. We work with industry, with educators, with CBOs, community-based organizations, and with government agencies to create workforce development programs for 21st century careers. And so my background, I'm not an educator, I'm an industry guy. I've got 40 years in telecommunications. And what I'd like to talk to you today about is the smart grid workforce, what's going to be driving that, and basically, how many of you know what smart grid is already? Wow. Almost nobody knows what that is, at least in terms of being able to articulate it clearly. I'm going to kind of define that for you, just in terms of the problems with today's grid and how smart grid proposes to solve those problems. So, I guess the best way to start is, any of you remember what happened on September the 8th at about 3:30 in the afternoon in 2011 in San Diego? We had a blackout, didn't we? What was happening was that we had there was some work being done at the Yuma, Arizona substation, and a fault occurred, and within 30 minutes, power was out for 6 million people across Southern California and northern Mexico. So that's one of the interesting things about today's grid, is that sort of thing can occur, and it's not necessarily an isolated incident. So here's what we think happened. It's still under investigation, but here we have a technician doing some work at the Yuma substation. That fault took down a 500 kilovolt line that connected Arizona to the western grid, the western region power grid. That then caused widespread outage here, and as you can see in the background here are a network of control centers that people were trying to fix this. Like, what the heck happened here? So, and they couldn't figure it out. So you got people in control centers in 6 different locations who had different software, different operating systems, no visualization tools in common, couldn't see each other's databases, and so it was just mass chaos. It took 12 hours to get this fixed. So that's one of the reasons you need smart grid, is to prevent that kind of thing happening. So we'll go through some steps to show you what that's about. This, of course, was a very costly outage. This is what the estimate is on the economic impact to the region. $97 to $117 million just in those 12 hours that the grid was down. This is cost to industry and cost to the utility for overtime and restoration and so forth. So it's pretty all-encompassing. There were some uglier side effects that you don't normally think about. Something like 2 million gallons of raw sewage was dumped into the clean water supply, or dumped into channels that fed the clean water supply, because the pumps stopped working, right? You need electricity to run the pumps. The pumps start working, raw sewage gets overflowed into these channels, and probably the most ironic of all is 125,000 gallons were dumped into a canal called Sweetwater. So, these kinds of things make you realize we really need something better than what we have today, right? Outages are one thing, the drinking water is another. But there's more. So that's a problem that we need to address with smart grid, and it's basically an ICT problem. It really is. It's information and communications technology all over this. So here's what could happen to you. You just bought a new plug-in Prius hybrid, and 9 o'clock at night you had a nice new charging station installed in your garage. 9 o'clock at night you plug this thing in and your lights go out, as do the lights on the rest of your block. What do you think happened? Transformer blew, right? Because if you have multiple of these plugging in at the same time or being charged at the same time, the transformer can't handle it. Today's transformers cannot handle that. So that's an issue that needs to get solved with smart grid. Here's another. You just installed several $1,000s worth of photovoltaic cells on your roof, and the inverters and the entire system to support that. And so this is the kind of power output that you get from that. You notice it's time of day, it's shading, it's all sorts of clouds, trees, etc. In many cases, your utility won't allow you to connect this to the grid. In other words, you have an island that you've created that you can draw from the utility and you can draw from your own power source, but you can't feed power back into the grid. Why is that?
Well, you don't want to shock somebody who's working on it.
That's a good point. That's a good point. The other problem too, though, is that the grid doesn't have the intelligence to deal with a highly variable energy source like this, right? It's used to having hydroelectric turbines, that produce, or nuclear reactors that produce a fairly steady energy source. This kind of thing, I hear people, like the chief engineer at San Diego Gas Electric said, our engineers have been designing circuits out of lookup tables for all these years. They don't know how to engineer anymore. We need engineers who understand stochastic probability. I don't even know what the hell that is, but I remember the term because it's just like, okay, that's a pretty big thing to learn, and this looks like a pretty difficult problem. You need smart grid to be able to integrate this energy source back into the grid in an effective way. So here's another deal. You can see a line plot of energy usage versus the bars that indicate what the prices are. So you can see that there's dynamic pricing here. There's a standard pricing structure for electricity that you use in your home, and there's a dynamic aspect that's represented on critical days and peak periods. So you look at that and you say, well, I would really like to use less energy when the rates are lower, but your family doesn't always cooperate with that, right? I mean, they want the air conditioning on, they want the pool pump running, they want, do laundry at certain times. So that's kind of a problem. How do you manage your own usage to take advantage of low rates? Any thoughts? Anybody? Yes, sir.
Well, what they have an option out for is a rate structure where you pay more if you use it during peak time. But the fundamental problem is the current grid cannot keep the excess energy anyway, right?
Right.
So they can't generate more earlier and use it in the afternoon.
Exactly. That's a good point. So I think you've started to sum up this slide here, which says, plug-in hybrid electric vehicle, overload, high cost, an island of renewables, where several of these are solved by, these two are solved by energy storage, right? So this is an energy storage system that you might find in a substation. The other part is automated demand response. So if you can imagine having a network within your home or within your business that's like a Wi-Fi network, where you have intelligent appliances, intelligent thermostat, and you have RF communications among those, where you can automatically manage your usage so that you're using less energy during these peak periods. All right? So, and guess how this gets accomplished, right? It gets accomplished with information and the ability to communicate that information to systems and people who know how to deal with that. So here's another problem. One of the things I forgot to mention about the San Diego outage was that there was the voltage dropped dramatically in San Diego at the San Onofre nuclear reactor plant. So a lot of us think about China syndrome and things like that, but that voltage was so low that the San Onofre power plant actually went offline. because the quality of the power was so low. The same thing happens in a manufacturing environment. When the quality of power is so low, pumps start shutting down, motors start shutting down, industrial processes can shut down, or at least be slowed down, impaired, etc. by poor power quality. So that's an issue for our economy in terms of the electric grid having a negative impact on the productivity of some of these manufacturing plants. So here we have a similar kind of thing that's a solution for industrial commercial. They have same kinds of problems here, putting in renewables and managing costs through demand response capabilities, but they also have production losses that result from poor power quality. So smart grid puts in things like power quality control, so that you have an appropriate phase angle, that you have voltage control, etc. I mean, all controlled through information, timed by GPS receivers, things like that. So it's very, very precise timing. And again, with energy storage and demand response. So there was one other point that was mentioned, I think, who said transformer, right? Plug in your electric vehicle, blow the transformer. Another piece that's happening is that we're beginning to get intelligent transformers that can be communicated with by the network and evaluated at a control center, and things can start shutting down. So again, more information control, even at the transformer level. All right? So now I've taken you through all this, and I've taken you through it pretty fast. So let me just stop and see if you have any questions at this point. No? Okay. So here's another problem. Remember we mentioned we have 6 different regional centers that we're trying to solve the San Diego outage last year. The problem is that these systems are extremely complex. Each regional center has grown up on its own, has its own database, has its own graphic displays, has its own tools. It has, they're not similar at all, so they can't talk to each other. So there's very little coordination except what the human factor can accomplish among these players in the grid. Another issue with the grid itself is security, the grid control system. Meaning, how many of you have seen the movie Live Free or Die Hard with Bruce Willis? Right? Love that movie, right? Yeah, but we don't want to have Bruce come save us every time that somebody tries to hack into our system and send all the natural gas in the region to one point where it's going to explode. So we need better security of the grid itself, and so that's a major issue that needs to be solved, especially in times when you have homeland security measures and priorities and imperatives related to the electric grid. So once again, we have a number of problems that are solved in different ways. Cascading failures, self-healing architecture. How many of you are familiar with the telecommunications network that the carriers use today, right? So self-healing, that's part of it, right? Synchronous optical network, or SONET, here in the U.S. Anybody from outside the U.S.? Synchronous digital hierarchy from in the rest of not outside of North America. Those were intended to be self-healing, and they are. And it's a direct corollary between what was accomplished in the telecommunications environment and what's going to be accomplished by smart grid. A lot of communications overlay, new sensors, new technology, communications overlay, and some database management and visualization that can be done to prevent these cascading failures. That, of course, will require us to do something about this complex interconnectivity. And what I mean by that is we need more similarity among the way these nodes are configured that are managing the grid. And of course that means more commonality among database management systems, more common visualization tools, and more data analysis capabilities. And then of course cybersecurity, which I think most of you have been reading about already. Any questions on this in terms of the overarching big problems of the grid that we need to solve? Any questions? Okay. So, what does this mean financially? Obviously, there's going to be costs associated with upgrading to a smart grid. But you can see some pretty impressive organizations here have weighed in on quantifying that. $1.8 trillion added to the economy by 2020 through a more reliable grid. Where do you think that money, where that economic impact is coming from? Is that revenue to the utilities? Where do you think that comes from? Savings?
To the companies that are using electricity.
That's right. So it's, remember the production throughput problem that we talked about before from poor power quality? So that's part of it. A part of it is also lack of a need to duplicate equipment and systems, so a lack of, a reduced level for capital expenditures. And some of it is about workforce, because you're going to automate quite a bit of the workforce, or quite a bit of the tools that the workforce uses.
I have a question.
Yeah.
What assumptions does this make on the increases of electric cars?
Electric cars?
Yeah, more electric cars.
I'm sure that's in there somewhere. I've read the report. I don't remember that particular aspect, but it's in there. It does. I mean, the fact is, it's really not possible to incorporate electric cars on a mass scale without smart grid, right? And so, does this include the dollars spent for charging stations and for new cars and things like that? I don't know. So embedded in this number is this number here, $49 billion, which would reduce the cost of power outages, similar to the one we saw in San Diego last year. I've seen this actually be as high as $120 billion a year. So there are numerous studies about that. I just chose the most conservative one. And then if you just talk about, saving the planet, CO2 reduction, renewable energy, plug-in hybrids, energy efficiency. Does anybody know what demand-side energy efficiency is? Does that term mean anything to you? So it's the demand side of the meter, the customer side of the meter. So if you think about smart grid and the electric utility grid, that side of the meter, and all the technologies that are being deployed there, similar kinds of technologies are being applied on the customer side of the meter as well. If you can imagine, demand response is going to require quite a bit of infrastructure on the customer side. Okay. So, here in California, there's a law called AB 32, Assembly Bill 32. It was passed during the Schwarzenegger administration, and you can see what the goals are here. Reducing greenhouse gas emissions by 30%, achieving statewide energy mix of 33% renewables, okay? And that 33% has to be wind, solar, and biomass. It cannot be hydroelectric, and it cannot be nuclear, right? So it's not just other than fossil fuels. It's absolutely new technology kinds of sources. And cap and trade, which allows people to implement, to buy credits if it's not financially feasible for them. For companies that have already made energy improvements, they get these credits, which can then be sold to companies that can't, for whatever reason, make the upgrades at that particular point in time. But the impact of all this is that in California alone, we're looking at, by the year 2020, a $33 billion increase in economic production and 100,000 new jobs. And by the year 2050, this whole AB 32 is designed to reduce greenhouse gas emissions to 80% of 1990 levels, which is pretty aggressive, very aggressive, as a matter of fact. Questions?
You said wind, solar, and
Biomass.
Biomass.
Yeah. Yes.
Earlier you said that fewer jobs, one of the savings from the smart grid would be that the fewer jobs, I guess in the production of the electricity.
Right.
Because things would be automated,
Right.
but now this does 100,000
Right.
jobs.
And we'll get into that, but there's a shift, just as you saw you've seen with ICT over the years, there's been a shift in where the jobs are. So yes, the traditional jobs are, and I have a chart that shows you this later, traditional jobs will actually decline, some of the newer jobs will be increasing.
Do you know which will be more?
Yeah.
Will end up the net will be a net gain in the end?
Yeah, I'll show you that. Okay. And it won't be job by job. I don't have that data in this presentation, but I can show you which parts of the industry the jobs, where the jobs will be affected. Okay. So also within AB 32 is a workforce policy that says California will have a green technology workforce to address the challenges and opportunities presented by the transition to a clean energy future. Now this is actually a mandate that's managed by the California Public Utilities Commission. They actually have a strategic plan for energy efficiency in the state of California that goes out 20 years. And so that plan has workforce embedded in it. So there, if you want to look at what the CPUC says we're going to do about workforce, it's in their strategic plan, which is on their website. I think it's called the Long-Term Strategic Plan for Energy Efficiency, is the name of it. So kind of gone through what smart grid is at this point, and some of the basic impact areas that we see, and some of the economics associated with it. So now let's talk a little bit more about skills requirements, how it's going to evolve, what the skills requirements are. We'll talk about workforce development initiatives and go from there. And jobs. So just to sum up, this is what smart grid is traditionally viewed to be, where it's a continuum of energy generation, self-healing network capabilities, cap and trade electricity market enabled by cap and trade, demand response that allows you to manage your usage. Oops, sorry, I've got a fat finger here. I had a little surgery earlier this week. Energy efficiency to make the grid more efficient. Do you know that the grid, the electric grid, is only about 40% efficient? That is, only 40% of the electricity that gets generated and delivered by the grid reaches or serves some useful purpose at the other end. The rest of it's wasted through heat or lost energy from other means. Anybody surprised by that?
No.
No? Okay. Thank you. Yes.
That doesn't include all the devices we have in our homes that are not efficient with the energy that reaches us.
That's correct.
VCRs that flash, devices that flash.
Flash, yeah.
We don't want to see.
Right, yeah. Some of that is inside the circle. So microgeneration, which is renewables you might have on your roof, smart meters, which are on your home or on your business, and microgrids. Does anybody know what a microgrid is? So microgrid applies typically to a large building or to a campus. So a community college or university might have, is anybody from Foothill College? You are? Oh, good. So Foothill College has a microgrid. You've got parking lots with PV arrays, and you've got inverters and all sorts of monitoring and management equipment inside your buildings. And so you're capable of actually disconnecting from the grid, right? And generating your own energy source. So you're sort of using the grid as battery backup, if you will, right? To use that analogy. And so there are other colleges and universities. The military just announced that several hundred of their bases are going to microgrid configuration, which is kind of interesting as well, where you're generating your own energy, such as a PV source. Did anybody drive out Interstate 580 through Tracy Everybody notice by the Safeway distribution center there are a couple of big wind turbines. So here's Safeway developing their own energy. They have a microgrid. They're capable of disconnecting from the grid right there. Yes?
I have a misunderstanding of cap and trade, going back there for a second.
Yeah.
Would they be free to throw out the cap and trade, because doesn't that just pay for hydrocarbon usage?
Well, what it does, yeah, you know, it's sort of a counterintuitive thing, isn't it? What cap and trade does is it realizes that not every industry and not every business can convert to a more energy efficient operation all at once. So those that commit that are contributing to the energy efficiency and lower CO2 emissions can actually receive credits which they can sell to others but those are limited time only, right? You have to keep buying those over and over again. So the ones who don't convert immediately, eventually are going to have to convert. It allows you to defer your investment, recognizing how companies operate, right? You can't always invest, everybody can't invest all at the same time. Power quality, we talked about. You know, and storage, right? Storage to use electric power that's generated from wind or solar, and to smooth out those curves in generation that occur from self-generation. So those are basically the elements of smart grid right there. I think it's kind of interesting that they put this in a circle because this is really the ICT connectivity among all of these elements of smart grid. It doesn't work without the ICT elements. So what do I mean by that? This is a really busy chart. And I hate standing right here. I guess I can. This is okay. I'll deal with it. So basically what you have along this line is generation, transmission, and distribution of power to residential, commercial, and industrial customers. Here you have solar farms that are also generating electricity to serve these customers. Transmission, so what do the transmission lines look like? Anybody? You can tell transmission lines because these are the ones that are really high up, you know, huge, big towers. They usually have these little red balls on them. Yeah, exactly. And distribution, so typically when you see these fenced-in areas that have, you know, lots and lots of big wires and boxes and coils and so forth, those are distribution substations. So this is very, very high voltage. This is still high voltage, but not in the 500 kilovolt range like that might be. So today, you have transmission control centers, you have distribution control centers that look at these things, and they use a capability called SCADA. Does anybody know what SCADA is?
Supervisory control.
And data acquisition. Right. Okay, so this is basically the telemetry network that collects data from all the sensors of these devices down here, and then communicates via these SCADA lines to transmission and distribution control centers. All of that's going to get an upgrade. Who said they were familiar with SONET, synchronous optical networks, right? So it's kind of the same thing where there's a whole new overhead layer that's involved in communicating among these devices. So let me just give you an example. From your meter to back to the utility. And I don't want to get into the controversy of smart meters, and that's not my area of expertise, but just to give you a technology data point. When you had meter readers, how often did you get data from that meter on the side of your house? Once a month. Okay? How often do you think you get it now? You get it down to the minute, yeah. So think about the exponential growth of data within the network just from smart meters. And then if you're going to control power quality, and if you're going to control intelligent transformers, and you're going to control the distribution, automation, automated demand response, think of all the data you're going to have from all these data points here. So you need a much more robust data communications network. So there'll be, essentially a private internet serving PG&E that collects all this data and routes it to the right sources here, and it's massive amounts of data. I mean, it's exponentially more data than they have today. So, any questions about this? Sorry. So that takes me to who are the players in this market. So you look at this and you say, well, here's home energy management systems like we talked about before, similar to a Wi-Fi network in your house, but to control the power. The same thing for building energy management in commercial and industrial buildings. Smart meters, advanced metering interface is what that means, AMI. Demand response, which we talked about, that allows customers to more real-time manage their consumption of power. And then you have management of the grid itself, distribution system, and this supervisory control and data acquisition network, which is the private internet that we talked about. And then grid interconnect. What in the world could grid interconnect be? Remember the control centers, right? So we got multiple control centers managing the western region, and to keep Bruce Willis from having to be on call all the time, we're going to need to do a better job of interconnecting those control centers. So that's what we mean by grid interconnect. This is the way the investment is expected to happen. Right now, we're kind of down here below the knee of the curve. AMI is, automated metering interface. I'm sorry, advanced metering interface. Distribution grid management. This is where you start, putting in energy storage. This is where you start putting in intelligent transformers. You start putting in new sensors to manage different parts of the network. And then you start implementing demand response, which is basically software based on what may be in a building or in a home, reacting to the grid. And then extended utility roles, such as being able to be looking at, and I don't even understand what this means. I'll just be honest with you. I could send you the report if you want. But basically what we're talking about here is that we're very early on in this whole phase of smart grid deployment. This is expected to go on for the next 20 years. As you can imagine, this is a huge, huge upgrade that's required. And the utilities are committed to this. I mean, there's something like, in California, there's like $5 or $6 billion worth of capital projects already underway for smart grid among the investor-owned utilities. Does anybody know what I mean by investor-owned utilities? Investor-owned utilities are those that are not municipal utilities. So it's going to be PG&E, publicly traded companies, PG&E, Southern California Edison, San Diego Gas and Electric, and Southern California Edison. So those four are the ones that are primarily going to be implementing smart grid according to this curve. You probably can't see this, but let me point out to you that this is the value chain just for smart meters and for the network that supports smart meters. So it's got people in here like, E-meter that you may have heard of, and you've got Itron, you've got Silver Spring Networks. All these folks are people who actually manufacture smart meters and the RF networks that support them. But then you have Cisco and IBM and Oracle and GE and AT&T and Microsoft. Why would you have all these players in here? Communication. Communication. I mean, look how communication rich this is, for those of you who can see it. Highly communication. Why would Oracle be in here? Database. And so, what makes this interesting to Oracle?
It's a huge database. That's what their software is built for, is analyzing the huge databases.
Right.
Producing analysis that you can do something with.
Exactly. So that's when you get into this whole grid interconnect system of connecting these centers together. How about an individual utility? Oracle is also in the business of enterprise resource planning, right? Which means all the applications that manage your accounts payable and accounts receivable and payroll and inventory and all of that. What is an electric utility? What would the enterprise resource, beyond those items I just mentioned, what would an enterprise resource planning system look like for a utility? It would look like dispatch, right? It would look like asset management, right? Where are the assets? You know, these are all things that Oracle is very interested in. Smart grid is going to essentially change the ICT landscape of these utilities. I mean, over the next 20 years. So that's why Oracle is there. They see themselves as being at the center of that and being the enterprise resource planning company for the utilities. Critical skills areas. So we're going to talk a little bit about that. Acronyms across the top, a lot of acronym soup here. GIS, grid interconnect systems, right? Connecting these control centers together. So look at the kinds of skills that people have to have here, right? AMI, advanced metering infrastructure, right? Smart meters. Operations management system. Demand management system. Demand automation, SCADA. So you can see, look at the software intensity and the communications intensity with the basic functions of smart grid. And this is from some newsletter I picked up. But I've seen this in other places as well. Interesting, huh? Any surprises here? Yes, sir.
Again, maybe I'm old fashioned, but there's no electrical technology listed here. You know, it's like we're measuring something which is, controlling something which we don't know about. You know, but this is an electrical system. Why isn't that present?
It is. And I've biased this somewhat for this audience, knowing that you'd be interested in the ICT stuff. So we'll get into the actual jobs in a moment. Okay? Anybody else? So how are the utilities going to roll this out? It's going to be real interesting, because what they'll do is they've filed, the investor-owned utilities, or IOUs, have filed smart grid technology rollout plans with the California Public Utilities Commission. PG&E, for example, has 21 projects that they filed to say, here's what we're going to roll out for technology, and here's how we're going to manage it, including how the workforce piece is going to be done. And so here's what they're doing, is for each demonstration pilot project, 21 in the case of PG&E, they have all of these different occupations involved. You know, engineers who are planners, lab test technicians, engineers who are site-specific, engineers who are more architecturally oriented. You have people who do installation, commissioning, operations and maintenance, evaluation. One thing I left off of here is customer service reps, right? Somebody's going to need to interface with the customer. So what they're doing is they're saying, why don't we embed our training organization, or an outside training organization, with each of these 21 demonstration pilot project teams. So you have a vertical slice of the workforce specifically aimed at, say, electric vehicle chargers, or energy storage, or some vertical application like that. And so this embedded trainer finds out all the things he can from the vendors, because the vendors will do some of this training. They'll also help with the workforce design. They'll also capture the skills that are needed and begin creating that curriculum so that when these projects go to scale, mass deployment, you have the curriculum already in place and ready to apply, to, say, electric vehicle chargers when that starts to roll out on a mass scale, right? So this is kind of an interesting difference. People used to go to get, a certificate or a degree in, electronic power systems technician certificate, let's say, right? Or electrical engineering for power systems. This is a little different in the way this is going to roll out. And so what does this suggest to you in terms of, as educators, how you have to think about this? Because the plan is that when it comes to this, scalable training, the public post-secondary system will be asked to do that. Okay? There'll be funding for it, we believe. And there's probably opportunity for development of curriculum here, funding to deliver the training. But what does that mean? When you've got a workforce that's, all they care about, this slice of the workforce, is electric vehicle charging stations. What does that suggest? It suggests that the training becomes a lot suppliers, the supply chain, and this thing called ESCO. I haven't talked about that yet. Anybody know what an ESCO is? Yes, sir.
Well, it's energy. It's a company that essentially uses energy. They do improvements in efficiency, and as a result of the improvements, they make an investment in improving the efficiency. As a result of that investment, they actually share in the savings.
That's right. So they look like aggregators, and they look like systems integrators in normal ICT parlance, right? So that's the profile they have. So that's interesting. Look at where the jobs are going to be. This isn't necessarily where the utilities have been focusing. They've been thinking about their own, upskilling requirements here, and there's been very little focus on the rest of this. Those of you who know John Carice from the Centers of Excellence and Julia Lindstrom, who's his counterpart in Southern California, they're actually beginning to research this. So within 6 months or so, they're going to have a handle mostly on these kinds of jobs, not so much on the utility side. Okay? And so here's the other thing that's happening. If you look at the utilities, look at the attrition rates that we're talking about here. And this is nationwide, right? So nationwide, look at the attrition rate. 43% of PG&E's employees will be eligible for retirement in the next 5 years. You've been saying that for the last 3 years. People's 401ks have been, they're not retiring because their 401ks aren't worth enough for them to retire. But these are some big numbers, and this is a big loss of competence within the utilities that will need to be replaced. And they have some very ambitious programs to replace that knowledge, not necessarily the people, but the knowledge. So if you look at non-utility career fields, you can see what's here. I apologize for a fairly busy chart, but you can see the kinds of jobs that are going to be affected within the different elements of that bar graph I just showed you. So now, there are questions. I can talk as long as you'd like. I guess we're effectively shut down here in a couple of minutes, right? Yeah. Yes, sir.
Yeah, I'd like to sort of sharing have sort of I come from the northeast of Alabama that has a Department of Energy grant for developing energy utility technology. programs, technicians who essentially was designed to essentially be the power line workers, utilities. And in a recent meeting, and so we're in the first year of that program, and in a recent meeting with National Grid, our partner in the institution, they told us things have changed. Okay, they're not going to be hiring any law graduates anymore. Okay, this program which has gone on to Massachusetts schools for the last 3 years to deploy. And they're saying, no, we're going to use contractors to essentially do a lot of work that our line people have been doing out there. And they're saying, however, you've got to look for opportunities for contractors and also smart grid skills. Okay? So they're redefining their own environment. Okay? I'm wondering whether that's true. Well, the other thing they mentioned, I want to put this out, is that gas is important. Is that because it's distributed generation, a lot of the distributed generation are going to see a natural gas base. Okay, so we have to have a workforce that can work with natural gas sources and controllers.
Those points you make are valid. It sort of varies from company to company when they're outsourcing their line workers and utility workforce at the technician and skill craft level. But yes, that's happening in many places. And when I talk about grid, I typically talk about the electric grid because that's most easily understood. But gas is equally important. I mean, if you look at the percentage of energy efficiency to be derived from the gas distribution, it's, on a percentage basis, it's equal to that of the electric grid. Are we done?
Okay,
So thank you so much. I appreciate your time. I'm happy to stay after this for more questions if you like.